Imagine you're trying to walk up some slope and you want to know, well, what is the steepness of our slope here? How steep is this? And you've probably experienced at some point that there's a steepness that's just too much. There's some point where something's just too steep that you just can't climb it anymore. And this steepness, if it's linear like this, like a straight line, something you learn in algebra is the linear function, where m is the slope. M is this steepness that you would be standing at. And that's all good for a linear function. But the question we're going to try to answer now is, what is this like, though, if you're walking up a curve? What is the steepness here? So let's take our picture, our linear steepness that we're walking up. Here's our curved steepness that we're walking up. And I have these people perfectly aligned here. So if we call this steepness slope m, which it is for a linear function, then is this steepness also slope m? And the answer is yes. But how do we determine that? I'm just connecting steepness with the slope of a linear function. Certainly none of that applies to something that's curved. You know, a curved function doesn't have just one slope to it. But what if each individual point of a curve had a slope to it? So let's go back to something you're familiar with from algebra, good old linear function. And when you developed that, you probably did rise over run. And to connect mathematics to this, you probably defined an x1 and an x2, and then you drew these over to the y-axis to get the function outputs. And then this difference here was y2 minus y1. This difference here, x2 minus x1. And from that, we define the slope, the steepness of this line. What we're going to do is we're going to use this exact same formula for slope on a curved function. So exactly the same setup as the linear function. And we want to know, what is the slope at x1? What is this slope here? Now, if we just apply the slope formula to the information given, the slope formula will give us a slope that connects these 2 points. So the slope of this blue line is given by the slope formula. And in general, we call this the secant. Oops, ran out of space there. And what we're going to do is x2 is we're going to start moving this closer to x1. Notice anything? Look at it this way. Imagine we have our curve. We've got our person standing here. They're at some steepness, some slope. I'm going to do the same setup I just showed. But now I'm going to draw another person on this slope that we're getting. And as we get closer and closer to x1, notice that the steepness of these two people will start becoming the same. It's almost as if they're standing on the same line. And if we label these people, just call this person A and person B, the process that's happening here is that the slope of person B is approaching the slope of person A. And this is where infinity is going to kick in, because we're going to get this forever closer, which means mathematically person B's slope will have the limit of person A's slope. So here's kind of a visual picture. Here's more of the math picture. So connecting this then to some math, what I'm saying here is approaching x2 is approaching x1. And remember, we still have the standard slope formula. This is everything you learned from algebra here, the standard slope formula. And what we're going to do is we're going to take approaching and combine it with the slope formula with the limit. So we're going to take the limit of the slope formula you learned in algebra as x2 approaches x1. So this slope formula that you learned in algebra, that is the slope for only linear functions. However, if we take the limit of that slope, we will then have the slope at a point for all functions. In other words, this only works for linear functions. For only linear functions will you get the correct slope. If we want to get the correct slope for all functions, we put the limit on there. Now, this notation is cumbersome to use because of all the subscripts here. So we're going to make a change of notation. We're going to take the same thing, but change this notation here. And let's go back to what you're familiar with the x1s and x2s. Is the first thing we're going to do is our point of interest. We're going to call this x. Instead of x1, we're just going to call it x. And instead of the y1, we're going to use function notation. So we're going to plug in x, and we're going to use f of x for the output. So function notation. Now this distance between x1 and x2, this distance we're going to call h. So if this is distance h, that means if this distance is x, and then this distance is h, then x2 is x plus h. We will again use function notation on this. So instead of y2, we will use function notation to get f of x plus h. So here is the slope formula you learned in algebra. And I'm going to simply substitute this new stuff in. Substituting all that in gets us this result. And I want to stress that this new expression is exactly the same formula you learned in algebra. It's just written in different notation. So now that we have this new expression, let's take the limit. So here's the expression we had previously. And then with the substitutions, we get this limit. And these do equal. But what's nice about this limit is h goes to 0 is usually a lot easier to work with than x2 going to x1. And this right here is a huge deal going forward. It's such a huge deal that it gets its own name. The derivative. This is the derivative. The derivative is the slope at a point. So you pick some point on a function, and the derivative will give you the slope at that point. It's also commonly called the instantaneous rate of change. Words that just mean the same thing in this context here. And because the derivative is such a huge deal, it also gets its own notation. And we call this notation f prime x. So that is an apostrophe there, but commonly said f prime of x. So not quite sure why that's called prime, but that's what's commonly said, f prime of x. That is the derivative, and it gets its own notation even. So let's check out an example, good old x squared again. And let's say we want to know, what is the slope at x2? Well, we've got our derivative, and we need first to figure out what x plus h is. All we're going to do is plug x plus h into the function. And when you do that, you then get x plus h squared. And we're going to take that, substitute it in for this. We'll also take x squared, substitute it in for this. And when we do those substitutions, we get this. Now, the overall goal here, what's the overall goal? The overall goal is to get rid of this h. Because as h goes to 0, remember, if you just plug 0 in here, you'll get division by 0. And that's no good. The goal is to get rid of this h. You don't want division by 0 here. And so that's what kind of guides you on with the choices you're going to make here. So our goal is to somehow get this h to divide out. And in many cases, this can be like a little puzzle game. The route forward may not be clear, and you have to try things. So what's something we could do here? Well, we could distribute this out and just see what happens. There's no way of knowing this will lead to the right answer. It's just something we can do and see if that'll get h to cancel. So if we expand that out, we'll get x squared plus 2hx plus h squared. And doing that, x squared and minus x squared will subtract out. So those will be gone. And in the numerator here, the greatest common factor is h. So we can factor that out. And now that we have these factors, they divide out. And here's our limit. And now, as h goes to 0, as this gets smaller and smaller and smaller, going to 0, what is this approaching? What is this forever approaching? As h goes to 0, this is forever approaching 2x. 2x is the derivative. And there is the derivative notation. So with our derivative, the original question was, well, what is the slope at x equals 2? Well, the derivative, with this notation, the derivative is a function that outputs the slope at every point. This function here outputs the slope at every point of this function here, x squared. These functions are related through the derivative. So if we want to know what the slope is at x equals 2, well, we just plug 2 into the derivative. And we get 4. So this may seem goofy, but it is what it is at this moment for this. But here's question 1 for the lecture homework. What is the derivative of f of 2? 4. So let's just run through this graphically. So here's our function, and here is the derivative of that function. And let's say we plug 0 into the derivative. If we plug in 0, we get 0 out. That means the slope at 0 is 0. If we plug 1 into the derivative, the slope at 1 is 2. F of 2. The derivative gives us the slope at every point on this function. So in summary, the derivative. So the derivative is such a big deal that it's going to be the rest of test 1. Test 2 will be all about the derivative, and test 3 will be all about the derivative. The derivative is hugely important. This is one of the huge chunks of calculus, the derivative. If you want to check out more of these problems being worked out by hand, then make sure you check out the practice 11.3. And the practice 11.4 will also be doing exactly this. I'll talk to you in the next lecture.